Let's imagine that we have a mass of 3 kilograms that is sliding to the right at 5 meters per second. And let's imagine that it slides a distance of 4 meters. To start with, let's imagine there's no friction. We have no non-conservative forces. How fast will it be moving over here? Well, it might be obvious, but let's just look at this carefully. What do we have? We have that the work done by the non-conservative forces is equal to the change in the mechanical energy. In other words, it's going to be the initial mechanical, the final mechanical energy, which is K final plus U final, minus the initial mechanical energy, which will be K initial plus U initial. Okay? In other words, we'll write this out. K final plus U final minus K initial minus U initial. Okay, there we go. First, since we're on a horizontal surface, the final potential energy will be the same as the initial potential energy. There's no change in height. So U final minus U initial, those cancel each other out. So we don't have to worry about that. And then the kinetic. If there is no work done by the non-conservative forces, this is going to be 0. So the work done by non-conservative forces is 0. And what do we have? We have that the final kinetic minus the initial kinetic is 0. In other words, the final kinetic equals the initial kinetic. So we know that the final kinetic energy will equal the initial kinetic energy. So what is the speed going to be? It's going to be exactly the same as it was here. It's going to be 5 meters per second. Okay? Hopefully that's not a surprise. Hopefully you could have guessed that right from the beginning. No friction. It's just going to be sliding along, not slowing down, no acceleration. It's going to be going at 5 meters per second. But now let's stick in some friction. Let's imagine that we have a coefficient of kinetic friction of, let's say, 0.100. So now we're going to have some work done. This is not 0. We're going to have some work done by the non-conservative forces. Friction. We're going to have some kinetic friction. So what is the work done by the kinetic friction? Well, in this case, we can assume that the magnitude of the kinetic frictional force is a constant. So the work done by our non-conservative force, we can go back to our original definition of work. Since we have a constant force, and it's only a one-dimensional problem, we can say that this is going to be the F dot dr, or F dot delta r. In other words, it's going to be the frictional force times the displacement. The displacement is now 4 meters, times the cosine of the angle between them. Now, let's think about that for a second. Our displacement is to the right. What is the direction of our frictional force? So, if the object is sliding to the right, the friction is to the left. So what is theta? What is our angle here? Displacement, delta r, force this way. The angle is 180 degrees. And what is the cosine of 180? That's going to give us a negative sign. So that cos 180, that gives us a negative. In other words, the work done by the non-conservative force, the work done by friction, is negative, which means we are removing mechanical energy from the system, removing kinetic energy in this case. Since the potential is not changing, we are decreasing the kinetic energy. Okay, that makes sense. It's going to cause the object to, what, slow down or speed up? It's going to cause it to slow down. That negative is extremely important. Coming from that cosine of theta, we've got to make sure to keep that in mind. All right, let's put some numbers in here. What is our frictional force? Well, we know that the kinetic frictional force is equal to mu k times the normal force. I'll put a capital N here. That's not the net force, that's the normal force. So what forces are acting on here? Well, we've got the frictional force this way, so this is Fk. We've got a normal force, Fn, and that is balancing the weight, which is mg. Let's be careful, this W is weight here for not work, so the weight is mg. The normal force is going to balance the weight, so the normal force will be equal to mg also. So our kinetic frictional force will be mu k times mg. In other words, mu k is 0.100 times m, which is 3 kilograms, times g, I don't have to look for it, 9.80 meters per second squared. We multiply that out, and what do we get? We get a frictional force of 2.94 newtons. So how much work is done by our by the frictional force? It's going to be negative Fk, which is 2.94 newtons times 4 meters, which gives us a work done of negative 11.8 joules. And that's going to be the change in our kinetic energy. Well, what is our initial kinetic energy? K initial is 1/2 mv initial squared, or 1/2 times m, 3 kilograms, times v initial, which is 5 meters per second squared. 1/2 3 times 5 squared. We multiply that out and we get 37.5. And what do we have? Let's come back here. The work done by the non-conservative forces is negative 11.8 joules. This must equal K final, the final kinetic energy, minus K initial, or minus 37.5 joules. Let's bring this over here, and we have K final is 37.5 joules minus 11.8. I'm running out of space here. I'll come over here. So K final will be equal to 37.5 joules minus 11.8 joules, which gives us a final kinetic energy of 25.7 joules. 25.7 joules. And that must equal 1/2 mv final squared. Solving for this, we have v final equals 2 times 25.7 joules divided by m, which is 3 kilograms. Take the square root, and we have v final equals 4.14 meters per second. So what is that telling us? The mass goes from 5 meters per second to 4.14 meters per second. Is it slowing down or speeding up? It's slowing down. Does that make sense? Yes, it makes sense. The friction is causing the mass to slow down. We've got a pretty low coefficient of kinetic friction, so it's not slowing down a whole lot, but it does slow down from 5 meters per second to 4.14 meters per second. All right, that makes sense. Very, very good. Let's ask another question here. Let's imagine it goes past that 4 meter point. Excuse me. From the initial position, how far will it go until it finally comes to rest? Let's ask that question. What is delta x going to be from our initial position where it was moving at 5 meters per second? How far will it go until the block finally stops? Let's see if we can figure that out. Let's come back here and see what can we keep, what can we not keep. We still have the work being done by the non-conservative forces equal to K final minus K initial. But what is K final now in this case? Over here, what is the final kinetic energy? If it stops moving, K is 1/2 mv squared, and if v is 0, K final will be 0. So K final is now 0. So what do we have? We've got the work done by the non-conservative force, the friction, which is, again, negative F times, oh, well, now our displacement is not 4 meters, it's going to be delta x, and we don't know what delta x is. I'll put this in a different color. Delta x. And we're trying to solve for delta x. And we'll end up with negative 2.94 newtons, that's still the frictional force, times delta x. But that must now equal the negative of our initial kinetic energy. And the initial kinetic energy is 37.5. So this must be negative 37.5 joules. So what's our displacement? Well, we can solve for our displacement right here. What is this telling us? The work done by the non-conservative force must be the negative of our initial kinetic energy. In other words, the object is losing all of its energy to the work done by the non-conservative force. So all of the kinetic energy is being lost to the work done by friction, and we end up with delta x equals negative 37.5 joules divided by negative 2.94 newtons, negative 2.94 newtons. Notice we've got a negative divided by a negative, which is going to give us a positive number, which is what we would expect. If we ended up with an extraneous minus sign, we would know something went wrong. A joule divided by a newton, well, remember a joule is a newton meter. We divide off the newtons, which gives us meters, and so that looks good for delta x. Delta x equals, divide that off, and what do we get? We get 12.8 meters. There we go. So the mass will slide a total of 12.8 meters, which is longer than the 4 meters we started with, so that makes sense. It's going to go further than that, which is what we assumed. And it's going to go a total of 12.8 meters until it finally stops, and all of the kinetic energy has now been lost to the work done by the non-conservative force. Great. Let's try another problem where we incorporate not only kinetic, but potential energy and some work done by a non-conservative force.